Okay, good evening and welcome to this evening's Physics P1 revision hangout for anyone studying core science. To make the most out of this, you'll need some paper, a pen and a calculator, as I'm going to ask you some questions throughout as we go along. If you're from Nodewood, feel free to ask any questions on the frog page. At the moment, there's a little hiccup with that. They might be able to be seen by other people. Okay, so just bear that in mind if you do want to post any questions, but feel free to post them as we go along. Anyone watching from YouTube, feel free to post any questions on the live chat and I'll go through as many as I can. So starting off then, I just want to talk about the equation sheet that you'll get for P1, because actually the equation sheet that you get for P1 doesn't have too many things to it. It has only 5 equations associated with P1. And for anyone in year 11 studying P2, you'll realise that you have much more to deal with in P2. So just 5 equations, and they'll give you the equation on the left-hand side, and on the right-hand side, they'll give you what the letters mean. What they don't give you are the units, and you have to remember these. So we're going to go through I'm going to model with you how to answer these equation questions. And basically you just need to use a highlighter in your exam. You need to know how to use your data sheet. And most importantly, you need to remember your units as well. So first of all then, if we're thinking about the type of things that we might be using in equations for P1, we can start to think about the units we might need to remember. So first of all, let's think about wavelength. What I want you to do is for all of these, try and think about the units and whether you know the correct units to put those into. I'll just give you 1 minute now to kind of speed through and try and write down as many of the correct units for all of these as you can. So power, frequency, specific heat capacity. So off you go, and then I'll come back in about 30 seconds and see how you got on. Okay, let's go through a few of them then. First of all, here we've got wavelength, and the word length in there should be a clue to you that you would measure that in meters. So, especially if you're doing higher tier, if you see something in centimeters, you might have to convert that to meters. Mass is measured in kilograms. So again, if you see something in grams, you might have to convert it to kilograms first of all. Time we'll come back to in a minute, and energy we'll come back to. We'll focus on speed, which is meters per second, temperature in degrees Celsius, power in watts, and frequency is in hertz, the number of waves per second. And specific heat capacity is in joules per kilogram degrees centigrade. Now with energy, time and power, actually, I want to talk about some different units that you might see. So normally we see power in watts, but probably for your P1 exam, and I'll explain why later, you'll probably need to use it in kilowatts. Okay, so it's different to P2 where you normally have to use it in watts. So just bear that in mind. Normally using it in kilowatts. And time, because of the equation we're using, often in science, we normally use seconds for time, but you just need to bear in mind for this one that the time unit in your P1 you may well see as hours. And I'll go through that equation and explain why a little bit later on. So if you're in year 11 and doing triple, bear in mind that normally time is in seconds, but depending on the question, you might have to use it in hours. And that brings me to energy, because there are definitely 2 units that you might use for energy in this topic. Okay, so one of those is joules, the standard units for energy that you might see. And the other one is how we calculate the energy used in the home, and that is kilowatt hours. And we'll look at that equation in a minute, linking energy, power and time. And you'll need to look out for this one where you're actually measuring the energy in kilowatt hours. and therefore you'll have to have your time in hours and your power in kilowatts. So just bear these in mind as you go through, and the thing to look out for, if an equation is 2 marks, it probably will give you the units already, but if the equation is a 3-mark question, then normally they haven't given you the units and you need to remember those for 1 mark. So just bear that in mind. Try not to lose an easy mark. So some people get really scared if they see questions like this in their exam. I want to model to you how easy they are to answer, because you can get, if you look back through the past papers, up to about 10 marks just by answering these equation questions alone. And I'm just going to show you exactly how you need to do that. So you need to get your highlighter in your exam or underline the key points. And you just need to read through the question, underline what they give you, and then select the correct equation from the sheet. So let's go through these 4 and then I'll give you some to do. So the first one says calculate the energy transferred to a 1.2 kilogram block of copper when the temperature rose by 15 degrees C. The specific heat capacity is 385 joules per kilogram degrees Kelvin. So all we need to do is write down what we've got. We've asked to calculate energy transferred. We've been given a mass. We've been given a temperature rise, and we've been given a specific heat capacity, which is there. Once you've underlined all those things, you just look for the correct equation, and you look along this side for the right words, and we find this equation here, E equals mc theta. This little symbol here is theta, but you don't need to worry about that. And we write that equation down. E equals m times c times theta. That's the first thing that you should do when you get these equation questions. And then all you need to do is put the numbers in. So E equals 1.2 multiplied by the specific heat capacity, which is 385, multiplied by the temperature rise, which is 15 degrees C. And then if you do that, you can work out the energy transferred, which will be 6930 joules. And in this case, in this equation here, our energy is measured in joules. So doing exactly the same thing with the next question, just a completely random question. Calculate the energy transferred by a 120 kilowatt microwave if it is switched on for 30 minutes. Give your answer in kilowatt hours. So do exactly the same thing. Have a look here for energy. And this is where you kind of need to know your units, because you need to know that kilowatts is a measure of power. So we have power here. And then we have time. And this is where your units become really important, because if you remember from the previous section, we said that that time has got to be in hours. So 30 minutes, we've got to convert to hours. So 30 minutes is 0.5 hours. These kind of things you'll see on foundation and higher where they've converted the units, but it's especially really common on the higher paper. So we just put that into our calculator. We just find the right equation first of all. So we need something with energy transferred in it, something with power, and something with a time. And you literally just look down this column and then find the right equation. E equals P times T. And then we just put our numbers in. So energy transferred equals power, which is 120 kilowatts. That's in the correct units. Multiplied by 0.5 hours. Now, if you're wondering how we know to put it in hours and kilowatts, you can just look at the units. It's asked us to put the units in kilowatt hours, and that tells you, therefore, that you multiply the kilowatts by the hours. So we do 120 times 0.5 hours, which gives us 60 kilowatt hours of energy. This is what I wanted to highlight from before then. We've just worked out energy in 2 equations, but in the top one, we've used joules as our unit for energy. And in the bottom one, we've used kilowatt hours, because kilowatt hours we use when we're talking about electrical appliances and things in the home. because that's how our units are measured on our electricity bills. Again, down here, calculate the speed, question 3, of a radio wave with a frequency of 300,000 hertz and a wavelength of 1,000 meters. So I want you to write all over your question paper when you get these. We've got a speed, which is the letter V, because I can already see it down here. We've got a frequency, and we've got a wavelength, which we use this funny symbol lambda. And then we just find the right equation, which is down here, and write it across. V equals F times lambda. So copy it right across onto your exam paper. And then we put the numbers in. So V equals 300,000 multiplied by 1,000 meters, and you will get an extremely large number. You will get 300 million meters per second, or you can write it as 3 times 10 to the 8 meters per second. Finally then, this efficiency calculation, again, people get really scared of these, but it's nothing to be worried about because you just underline the key points and answer the question. Calculate the efficiency of a light bulb that receives a total energy input of 240 joules and releases 120 joules of light energy. So we've been given efficiency, energy input, and some sort of energy released. So if we look over here, we've got 2 equations for efficiency, and we haven't got the words power in our question, but we have got the words energy. So we know to use this equation here. And in your paper, I'd expect you to write it out and then put the numbers in. But because I'm short of space, I'll just put the numbers in. So we've got efficiency equals the useful energy out, which is 120, because we said 120 joules of light energy is released, divided by our total energy in, which is 240, and then we times it by 100. And it says this weird thing here, times by 100%. So all you do is times it by 100, get your answer, which is 50, and then make sure you put the percent sign afterwards, because efficiency is measured as a percentage. So if you follow those few rules of just underlining the key bits, then referring to this paper, I will promise you, you will have up to 10 marks of your paper in the bag done. The only extra thing you need to look at is, are you using the right units? And remember your units. And also for higher tier, you will also, in some occasions, be required to rearrange the equation. Okay? Here's a few for you to have a go at then. So with your pen and paper, just have a go at these questions here. Just do the exactly same technique that I did, and I promise you, you'll do really well. So just look out for the extra little things with units. I'll check any questions whilst you are having a go at these, and then I'll come back and see if you got them correct. For those of you just joining, just have a go at these questions that are on the screen, and I'll come back with the answers in just a sec. Okay, just about one more minute to answer those questions, and then we'll come back and see if you got them correct. Okay, for those of you just joining, we're just going to go through these questions in about 30 seconds. So if you have a chance to do a couple, and then we'll go through and see if you got them right. Okay, let's stop there and go through the questions. Feel free to pause and catch up with me later if you want to have a go at these, or watch them on catch up when the video's finished if you didn't quite have time. So the first one says, what is the efficiency of a motor that converts 125 joules of electrical energy into 100 joules of useful energy? So we have a look what we've got. We've been asked to calculate efficiency, so we know it's definitely going to be one of these two. And then we just need to look at whether we're talking about power or energy. And if you look here, we're talking about energy. So what's the energy out and what's the energy in? So it converts 125 joules of electrical energy, so that's the energy going in. And then this here is the energy going out. So we use our equation, efficiency equals useful energy out, which is our 100, divided by 125, and then times by 100%. And you should have the answer of 80%. The second question, how much energy is transferred by 1.4 kilowatt drill in 1 hour? Give your answer in kilowatt hours. So we need to work out energy transferred. We've been given a power and a time. So we look down here for this equation, energy equals power times time. So energy equals our power, which is 1.4, multiplied by 1. And this time we don't need to change it because it's already in hours. So that answer is 1.4 kilowatt hours. So very well done if you got that one correct. Remember those weird units for energy when we're talking about energy in the home. This question said, if the cost of electricity is 5p per kilowatt hour, how much would it cost to run the drill for this time? So we've worked out that it's 1.4 kilowatt hours. So we just multiply that by our 5p to get 7p. And in the exam, just watch out, they might ask for that in pounds. So just bear that in mind and look very carefully about what they're asking for. If it was in pounds, of course, that would be 0.07 pounds. Next question on specific heat capacity. We've got the specific heat capacity of water is 4,200 joules per kilogram degree C. How much energy is needed to heat 1.5 kilograms of water from 15 degrees to 50 degrees C? So this one sometimes tricks people out. So you've got a specific heat capacity here. You've got a mass. You've been asked to calculate energy. And we've got something to do with temperature. So we know to use this equation over here, but people get confused a little bit by the temperature change. If you have a look carefully at what each of them mean, this theta here means temperature change. So you have to work out the temperature change first of all, which would be 35 degrees C. And then we put our numbers in. E equals the mass, 1.5, multiplied by 4,200, multiplied by 35. And that will give you an answer of, I'll write it over here. So I'm just going to move this answer over here. The answer would be 220,500 joules. So 220,500 joules. Excuse me. And then final question. Just down here, the final question. I've got a question about 2b. I'll come back to that in just a minute. Final question says, calculate the speed of a gamma ray with a wavelength of 4 times 10 to the minus 14 meters and a frequency of 7.5 times 10 to the 21. So we look at the information we've got. We've got speed, which is v, wavelength here, and frequency. So we need to use this equation, speed equals frequency times wavelength. So you'd have speed equals frequency 7.5 multiplied by 10 to the 21 and times that by 4 times 10 to the minus 14. Now, with wavelengths and speeds, expect to see these weird numbers here, so make sure you know how to use these on your calculator. If you're not, ask your teacher in school, because you will have to use these times 10 to the numbers on your calculator. And if you do that, you'll have the answer of 300 million meters per second, or you can write that as 3 times 10 to the 8 meters per second. And you'll notice that that was the same speed we got when we talked about a wave last time. So I just got one question that says, where did you get the 1.4 from on the 2b? So the 1.4 is from here, because it says if the cost of electricity is 5p per kilowatt hour, how much would it cost to run the drill for this time? So it's just 2b, so you'll find these kind of questions linked on to the ones that are just before. If it says how much energy is transferred by a 1.4 kilowatt drill in 1 hour, you've worked out the energy transferred, and it said if the cost of electricity is 5p, then how much would it cost to run the drill for this time? So we just take that 1.4 from up here and then multiply it by 5p. So someone's just mentioned that their screen resolution is a little bit funny for this video. That just might be to do with your internet download. So do let me know if other people find it fuzzy, but I think it's probably on the internet download. So moving on then, hopefully you got these questions right, and like I said before, you should be amazing at these now. You should be able to get those 10 marks or up to 10 marks in your question paper just by doing these equations. Moving on then to a bit of theory and a bit of something that sounds like it's going to be hard, kinetic theory. Your teacher might not have even described it like that in school, because it's actually something that is quite simple. It just describes the movement of particles in solids, liquids, and gases. So if we think about what we would describe the solid particles as and how they would look, here we draw a regular pattern of particles or atoms. And we need to think about how they're moving or the energy that they have. So if you remember with solids, the atoms or the particles are vibrating. This is important later when we talk about conduction and heat transfer. So the particles vibrate, and that's a little bit weird to think about because you're not necessarily thinking about all the solids around you and the fact that those particles are vibrating. Think about the atoms in your desk or in your computer. Everything is vibrating slightly because they have some energy. If we're describing the arrangement of these particles, and this has been a 6-mark question before actually, we can think about a regular pattern and the idea that they are close together. This is what the arrangement looks like, and this is the idea that particles vibrate. In terms of forces and bonds, they have strong forces in between the particles, which are holding that solid together. Then if we add a little bit of energy into this, we can melt the solid into a liquid. And if we think about how we draw a liquid, that's probably the most difficult one, but all the atoms are still actually close together and are rolling around each other. You don't want too many gaps in between here, otherwise you'll start making it look like a gas. So the particles in the liquids are still closer together. But this time, they've got not a regular pattern, but it's an irregular or a random pattern. So rather than being in rows like the solid, this is a very irregular pattern. The particles this time are doing more than vibrating, they're actually moving past each other. That's because they've got more energy now, they've gained energy, so they're actually going to be moving past each other. And they're moving randomly in all, they're not moving randomly in all directions, but they're moving past each other and quite randomly. Rather than in a solid here where the particles are vibrating, they're quite moving slowly and they're kind of rolling over each other. Compared to the solids, they've got weaker forces of attraction. That's why they can roll over each other rather than the particles which are just vibrating in the solid. Then if we think about a gas, those particles are far apart from each other. They're moving fast and randomly. Sorry, we can describe the liquid movement as randomly as well. So they're moving randomly, and these ones in the gas are moving fast and randomly in all directions. So it could be going over there or could be going over here. Is irregular in pattern, or they are is a random arrangement of gas particles. And they have weak forces of attraction between the molecules. That's why they can spread apart, because they're not particularly attracted to each other. Compared to the solid, there's very weak forces of attraction here. So this is kinetic theory. Something that sounds really tricky is actually a lot easier than you think. Then you need to make it. So just the idea of how the particles are arranged and how the particles are moving, and their forces of attraction between those particles. Okay, I'm going to move on now to some types of energy transfer, and these take up quite a lot of the course, so it's guaranteed that they will come up in some way. We've got conduction, convection, radiation, condensation, and evaporation. So conduction, first of all then. Conduction is the heat transfer in solids. So conduction occurs in solids, it doesn't occur in liquids or gases. And if we remember from before our arrangement of solid particles, you might think of something like this, a regular arrangement of particles all together. And if you were to heat up this solid here, the particles would vibrate more. Now, it's really important, I'm going to stress this, in the exam, you can't just say the particles will vibrate, because if you remember from just a minute ago, they are already vibrating. You must say that they vibrate more. That's really important. Seen on exam papers, they don't allow just vibrate, because they already are. But if you apply heat to a solid, they will vibrate more, and when they do, they will collide with their neighbouring atoms or their neighbouring particles. So if we're describing how conduction works, we're talking about the particles vibrating more and the fact that they collide with neighbouring atoms. And then they will then transfer their energy. So if you're talking about a 3-mark question about conduction, you need to get all of these 3 points in. The idea that the particles vibrate more, they will collide with neighbouring atoms or particles, and therefore the energy will be transferred. Now, you need to know about why metals are particularly good conductors. So things that conduct heat well, metals are good at heat and electricity, but we're talking about heat here. Things that conduct heat well are metal objects, so anything made out of metal. And the reason is because metals have something called free electrons. So in terms of conduction, as well as the metal atoms vibrating more and transferring the energy on, you've also got these free electrons, which I'll just draw as E's, which are allowed to move through the metal. And these free electrons also collide with metal ions and other electrons, and they transfer the heat energy. So if you can imagine, as well as these metal atoms starting to vibrate more and passing the energy, also these free electrons are allowed to move through the metal and transfer that energy. So really common idea in the paper as to why metals are particularly good conductors. So this is the first heat transfer method that we're going to talk about. You need to remember that it occurs in solids, and you need to remember these key words to be able to describe it. Secondly then, we are going to move on to convection. Now convection happens in fluids, and we call those fluids either liquids or gases. So you may well see a convection example in terms of air or some kind of gas, or you may see a convection example in terms of a liquid. So let's talk about it in terms of air first of all, and then we'll just relate it back to liquid. If you think about a radiator will radiate heat. That's not convection, this is radiation, which we'll talk about later. But it will radiate heat, and the particles next to the radiator will gain energy. These particles will then move slightly further apart. So because they've gained energy, they're moving randomly in all directions, remember, and they will move slightly further apart. And the fact that they move further apart means that they become less dense and they rise. So these particles rise up. It's really important, I've highlighted here, and I'm going to make a really important point of it. Do not in your exam write heat rises. If you go to write that, stop yourself. You can't say heat rises. You have to say, in relation to convection, that the particles rise, because it's these that are rising, not just heat. Okay, so you must say the particles rise, so they become less dense and they rise. And then at the top here, the particles will then collide with other particles and transfer energy. So when they get to the top of this convection current, they will transfer energy. And when they do that, they will come a little bit closer together again, and then they will get more dense and fall. And this will go back round in something called a convection current. So if you're asked to describe convection, you need to mention that the particles near the heater are gaining energy, they're moving further apart, becoming less dense, and they rise. Then at the top, they're transferring energy to the neighbouring particles, and then they become more dense and fall. So this type of energy transfer happens in convection, and you'll see it in liquids as well. So for example, here when we're heating a saucepan full of water, you will get these convection currents forming in the water where the particles here are getting heated. They'll get further apart, become less dense, rise, transfer energy, and then become more dense and fall. So that's our second form of energy transfer. You need to remember that it occurs in fluids like liquids and gases, and also you can excuse me, remember that convection needs particles. So just like conduction needed particles, convection also needs particles. Next then we'll move on to radiation. Now radiation is one that people get confused about quite a lot in the exam. So I just want to start off with a random object. And I want you to remember the idea that all objects are radiating heat and absorbing heat all of this time. And this heat energy is in the form of an electromagnetic wave. So radiation here does not need particles. It's how we get our heat energy from the sun. It involves infrared radiation, which is an electromagnetic wave, which comes up later in the topic. So I'll just put EM wave. And all objects are constantly emitting, that means giving out, and absorbing heat radiation. Okay, all of the time. Some objects are also good reflectors of heat radiation, which means that the heat will hit the object and reflect, or some of it reflect back off. And these are really important words for the topic of radiation. So just get that idea that it doesn't need particles like conduction or convection. It instead does not need any particles at all, and it's just an electromagnetic wave. So hopefully in your lessons you'd have looked about which colours are particularly good absorbers, emitters and reflectors. And again, this is really commonly something that causes confusion. So for absorbers, anything black, and especially matte black, which means a dull black, is a good absorber of heat radiation. And if you're good at absorbing radiation, you are also good at emitting it. So you're also good at giving it out. And this is what people get wrong a lot of the time. If you're a good absorber, you're also a good emitter. So matte black again is a good absorber of heat radiation. And then finally, you get some colours and some materials that are good reflectors. And those tend to be silvery objects. Okay, so I haven't got a silver, so I'll just write silver there. Silver objects are good reflectors. And the opposite to this is a white object. So if you had a white object, you're a bad absorber and a bad emitter. Okay, so these colours are important when we're talking about radiation, and that's our third main form of energy transfer. So just a quick recap: we had conduction, we had convection. They both required particles. This one was in solids, and this one was in liquids and gases. And radiation is our third one. That doesn't involve any particles at all. It is just a wave of energy. Now, the thing that they'll try and confuse you with in the exam is they'll often have questions which combine several of these all together. For example, when we looked at convection a little bit later, first of all, we were talking about energy radiating away from a radiator, and then we were talking about the convection current. So you really need to get the ideas of convection, conduction, radiation solid in your head so that you're not tricked out in the exam. Okay, whilst I check the posts on the Frog page and on the YouTube, have a go at these few questions. I've given you some marks to try and help you go along. I'll give you a few minutes to do these, and then I'll come back and see how you got on. Okay, just while you're having a go at these questions, just had a question about the free electrons in a metal for conduction. Can you call them delocalized electrons? Yeah, you could do. That's perfectly fine as well, whether you call them delocalized or free electrons. You'd get the mark either way. And the second question is about, is white a good reflector? Now, white on its own, we wouldn't class as necessarily a really good reflector because it tends to be shiny surfaces that are good reflectors. So if you had like a gloss white, a shiny white surface, that would make a good reflector, but maybe a dull white surface wouldn't be a particularly good reflector. So to be a good reflector, you need to be a shiny surface. So I'll give you a couple more minutes for those questions, and then I'll come back and see how you got on. Okay, for those of you who just joined, we're just going to have a go at these few questions. I'll give you about another minute to have a go at them, and then we'll come back and see how you got on. Okay, hopefully that's given you enough time to have a go at these questions. So these are typical exam questions that you might be asked. The first one says, why are blankets that are silver on both sides given to marathon runners? Okay, so if we're looking at 3 marks, we need to think about why are they asking us something about silver? So what about the topic have I learned about silver? I remember it's a good reflector and it's pretty poor emitter. So something that's silver on both sides, you want the idea that marathon runners, for 1 mark, want to keep warm after a race. And we want the idea that silver on the inside is good as it will reflect the heat back in. I'll just write it in shorthand here, but it will reflect the heat back in, or the heat radiation. And finally, the silver on the outside is a poor emitter, so it will reduce heat loss by radiation. So a typical question there, well, they give you kind of an everyday scenario and ask you to think about it in terms of what you've learned about these surfaces. Second question, which 2 types of heat transfer require particles? For that, you should have conduction and convection. Question 3, which type of heat transfer explains why a metal handle of a pan gets hot? Okay, and that is conduction. And question 4, solar water pipes are used in solar panels to heat water. Why are solar water pipes black? Okay, so if you have a look here, we've got solar water pipes using those solar panels to heat water for your house. Why are they black? Because black is a good absorber. And if you want to heat the water in those pipes, question 5 says, what colour would you recommend for the inside of the pipes? In question 4, then we perhaps recommend a silver surface because it is a good reflector. So if you want to keep the water inside, you might have black on the outside to absorb it, for example, and then you might have silver inside to keep that heat inside. Okay, so very well done if you got most of those questions correct. We're going to move on now and talk about a couple of more types of heat transfer, which are evaporation and condensation. So for evaporation, that is when liquid turns into a gas. So the transfer that you've got going on is a liquid into a gas. So for example, in this puddle here, puddles don't have to be boiling to turn into a gas. That's a common misconception that things have to be boiling to turn into a gas. They don't, okay? So if you imagine on a hot sunny day, this puddle will start to evaporate and turn into a gas. And whether the gas particles leave the puddle or not depends on 2 things. First of all, they've got to have enough energy to leave the puddle. But secondly, they've got to be facing the right direction. Because if you remember before, when we were talking about kinetic theory, these particles in the puddle can move randomly in any direction. So it's really important that to leave the puddle, they must have enough energy and they must be facing the right direction, okay, for this evaporation to occur. So this is quite common in the exam for 2 marks as to what conditions are needed for the particles to leave the puddle. For example, if this one down here had enough energy but it's facing downwards, then it's not going to leave the surface of the water. So there's a couple of key terms we talk about if we're describing evaporation. They quite like 3 or 4 mark questions on describing these heat transfers in the exam. And if we were, we'd need to think of the idea that in a puddle, you'd have several different particles, and they'd all have a different amount of energy. And I'm just going to give these random numbers to help us understand how we describe. So I'm just going to give these particles here random numbers. And if you think about it, you should be able to tell me straight away which 2 of those particles are going to be able to escape. Well, the ones with most energy, as long as these were facing the right direction, would be able to escape. And therefore they would be evaporated and outside of the puddle. And there's a couple of key terms when we're talking about describing evaporation that's really important. And the first one is that when particles leave the surface, so particles leave the liquid, and turn into a gas, but these particles are the ones with the most energy. So the particles with the most energy leave the liquid, and then the important thing is this then lowers the average kinetic energy of these particles left. So it lowers the average kinetic energy of the remaining particles. So this bit is really, really important, and I'll help explain it now by using these numbers. So the particles with the most energy leave the liquid, so let's assume these ones have now left. And as you can see with these lower numbers, that there would be a lower average kinetic energy of the particles that are left. So when evaporation happens, this is why it has a cooling effect, because the particles here with most energy are escaping and turning into a gas, and therefore it cools down the liquid that is left behind. And sometimes they ask this in relation to why we sweat during exercise, because the particles with most energy are escaping, and this lowers the average kinetic energy of the remaining particles so that you then cool down. Okay, so this is the cooling effect that is related to evaporation. So it's really important trying to get these key terms down in a longer answer question, and also remembering that actually to escape the puddle, first of all, you're going to have enough energy and you've got to be facing the right direction. So a little bit more than just understanding that evaporation is turning from a liquid to a gas. Opposite to evaporation, then we're going to talk about next, we're going to talk about conduction. And conduction is turning from a gas back into a liquid. So with conduction, sorry, I've just said conduction, I meant condensation, apologies. So condensation is turning from a gas back into a liquid. And that will happen on a cold surface. So if you imagine those particles that have just left the puddle, they're far apart, they're moving randomly in all directions. But then to condensate, to turn into a liquid again, those particles will have to lose energy, and they'll have to get closer together and turn into a liquid. So turn from a gas to a liquid. So that's exactly what happens, for example, on a window where you've got the hot water vapor particles in the air as a gas, and then when they hit the liquid, when they hit the window, they will then lose energy, become closer together and turn into a liquid. That's why you will end up with condensation on the windows. And you get more condensation on a cold day, because if that temperature gradient is bigger, you're going to get more condensation on the windows. So it's the opposite to evaporation, turning from a gas into a liquid, and the particles lose energy, get closer together, and therefore turn from a gas into a liquid. Okay, there are a few important factors that affect the rate of heat transfer and therefore affect the rate of perhaps evaporation or condensation. So the common one is looking at animals. So animals in the desert will have large ears, okay, because they need a large surface area to increase the rate of heat transfer. In other words, animals in the desert have large ears so that there's a greater rate of heat loss because they'll want to be cooling down a lot of the time. So these ears here are really large, okay, compared to perhaps something that it could have had, more like this size. You can see the ears are absolutely massive, and these big ears have that large surface area, which increases the rate of heat transfer. In a similar way, you will see something called cooling fins, and lots of people don't relate to what they are. So I've got an example here. If you see anything you examine in relation to cooling fins, you're talking about something in an engine with a massive surface area, so made out of loads of these. You might see it in a diagram form a little bit like that, a massive surface area to increase the rate of heat loss or the rate of heat transfer. Similarly, they might talk to you about the factors affecting the rate of heat transfer in relation to how long it takes for washing on a line to dry, for example. And there's a few key ones that we need to remember. And those are, as well as surface area, they are also temperature. So if you increase the temperature, like if the sun comes out, you will increase the rate of heat transfer and your washing will dry out sooner. Imagine if you had these clothes scrunched up compared to laid flat out. That's in relation to surface area. So if you had your t-shirt here scrunched up as opposed to laid out on the washing line like that, so you're increasing the surface area, this one is obviously going to dry quicker because it's going to increase the rate of evaporation in this case. When we're talking about a washing line, you want the water in there turning into a gas. You can increase the temperature as well. And also in relation to a puddle, another important thing is that you can increase the rate of airflow. That means as the puddle is evaporating from a liquid to a gas, you're going to have these particles then suspended in the air above it. And if there's not much air, if there's not much wind, then that means the rest of the liquid particles are going to find it difficult to escape because you need this kind of gradient here of the particles to allow those liquid ones to escape. So instead, if you had a windy day, if you had a big breeze here, which would take all of these particles away, you are going to get a greater rate of evaporation. So talking about airflow, but in relation to puddles, you might want to link that to just wind on the day. So all of these can increase the rate of heat transfer, including these specific examples for evaporation as well. Like I said before, it's really common to include examples as well as these animals, like these complicated cooling fins on cars, to increase that energy release. So that's a summary then of the last two bits of heat transfer, the evaporation and the condensation. And just remember that you also need to remember these things that affect how quickly those heat transfers happen. So here's a few questions for you to try. Have a go at these and then I'll come back and see how you get on. So I'll just give you a couple of minutes. So a couple minutes more for those of you who just joined. We're just going to have a go at these questions. Really common exam style questions that come up. Okay, just 30 more seconds and then we'll get back to it and check your answers to these questions. Try and get those key words like I was talking about in the last couple of slides into these answers. Okay, let's start here and think about the first question. It's a really difficult explain question. It says, explain how sweating cools a person down during exercise. So for the 3 marks, you want that first idea that the particles with the most energy leave or evaporate. Particles with most energy evaporate. And for the second mark, the idea that this lowers the kinetic energy, this lowers the average kinetic energy of the remaining particles. The remaining particles that are on the skin. And then for the third mark, just the idea that this will then cool the person down. As heat has been transferred. Okay, so the particles with the most energy evaporate and leave the skin, and this lowers the average kinetic energy of the remaining particles, which will cool the person down. For question 2, explain why a heated mirror does not steam up as much as a cold mirror. Okay, because there is the idea that there's less of a temperature difference then, or less of a temperature gradient, so there's less condensation. So I'll put the answer down here. So there's less of a temperature gradient, which means the difference between hot and cold. So you can have the idea that it's a similar temperature to the water particles. That might be fine. So less of a temperature gradient. Between the particles and the mirror. So the idea that there's less condensation or a lower rate of condensation. Okay, and the final mark then, an identical amount of hot water was put in each cup on the right over here. So let's assume it's about that much. And then it says which cup of tea, or should have been water, will cool quicker and why. So if you look at both cups, the same amount as water is in, but this will have a bigger surface area for evaporation. Okay, so we can say that cup B for 1 mark will cool quicker because it has a bigger surface area. And finally, so it has a higher rate of evaporation. So we've only covered so far, we looked at equations first of all, and then we've covered convection, conduction, radiation, evaporation, and condensation. You really need to know what all of these terms mean, because I guarantee there will be at least some questions on them in the exam. So now we're going to move on. We're going to still talk about heat transfer, but we're going to look at a couple of specific examples that you need to know about. And those are to do with this, which is a vacuum flask. And what I want you to bear in mind is in an exam, they might ask you about either a hot liquid in here or a cold liquid, because they work both ways. Vacuum flasks keep things hot, but they also keep things cold as well. And a vacuum is just a place where there's no particles, like in space. Okay, there's no particles in space, so you can't have conduction and convection. And that is what a vacuum is. And we'll talk about this in relation to heat transfer. So a vacuum flask then has loads of different designs which make it really good for either keeping the heat in or keeping the heat out. So first of all, it normally has a plastic cap. And plastics are good insulators. So they're the opposite to conductors. They are good insulators. So they reduce heat loss by conduction. So normally, if we had hot liquid in there right up to the top, you'd have the particles of the cap vibrating more and transferring heat out. But if you have it in plastic, that's a good insulator, so you reduce heat loss by conduction. You can imagine a question where they've got a metal cap and you might be asked, how could you reduce that heat transfer? By replacing it with a plastic one. So good insulators reduce heat loss by conduction. You've also got perhaps a vacuum around, which tends to be this area around the flask here, which will provide a vacuum. And if I've just told you over here that a vacuum is somewhere where there's no particles, you can think about what heat transfer that is going to reduce, because if you've got a vacuum, it stops any heat transfer that needs particles. So it stops or reduces greatly, if it's working really well, stop it, but reduces convection and conduction. So any heat that tries to be transferred by convection or conduction, that will stop. You'll also have other insulators in there, like the plastic case itself, which is a good insulator, preventing conduction again. You might have glass walls inside, which are a good insulator. And sometimes you'll also have a little plastic stopper here to stop any convection currents going around the outside. You sometimes have these foam or plastic stoppers here to reduce the idea of the convection currents going around and cooling it down. And also you have silvered surfaces on the inside. And if you remember from the VOR, why would they have silver surfaces? They would have those to reflect the heat, or reflect the heat radiation back into the flask. So that's if it's hot. If it's cold, it works in exactly the same way, but the opposite way around. Okay, so the silver surfaces would reflect any heat that would come in from the outside to stop it warming up. You'd have the plastic on the outside insulating it, so none of that heat from the air would be going in to warm up the flask. This plastic cap I'll just mention as well also will prevent evaporation and heat loss by evaporation. So that will keep the drink inside hot as well. So all those things associated with the vacuum flask, be aware they are commonly 6-mark questions, or at least multiple marks for these kind of things. So do try and write down all of these things to help you remember how they keep things hot and or cold. Moving on then, we're going to talk about heat transfer in the home. Okay, so heat transfer in the home, heat can be lost loads of different ways. So you can lose it through the roof, you can lose it through the windows, you can lose it under doors, through the walls, and loads of different ways that you are constantly battling to prevent or reduce heat loss in your home. And there's loads of things that you can put into place in your home to prevent this from happening. For example, you've got double glazing here, and I'm sure you can think of a load off the top of your head now. But you've got double glazing. Double glazing consists of a couple of panes of glass with a vacuum inside. And by now you should be thinking that a vacuum will prevent or reduce heat loss by conduction and convection, the two that need particles. Also, you have got roofs, for example, that will have insulation in those roofs. And that will prevent heat loss out of the roofs by both conduction and convection, because it will stop convection currents in your roof, and it will reduce the heat transfer by conduction up as well. In your walls, really importantly, I know we've gone over time a little bit, but I'll just finish off this section here. Through the walls, you have 2 layers of bricks when you build the walls, and inside you have a cavity in that wall. And yes, the cavity might have air in it, so that might be a good insulator already and reduce the heat transfer. But you can get in these cavities convection currents, which are going to take the heat from perhaps your lounge up to your roof and out of the side of these walls. So what they do now is they actually put cavity insulation into the walls and they'll fill it up with foam. And this prevents or stops those convection currents. So cavity wall insulation, you might even have it in your house now, reduces heat loss by convection. And also is often made of foam, which has got loads of air pockets inside. And air is a good insulator because it hasn't got particles close together. And as it's an insulator, it also reduces heat loss by conduction as well. A couple more to look through. We've got draft excluders that can go at the bottom of doors. And they prevent heat loss by convection. Because if you remember in convection, you have that cold air coming in, and if you have a gap under your door, you have cold air coming in to take the space of that hot air that has risen up in the convection current. So these prevent heat loss by convection by putting something to stop that air from rushing into your door. And also you've got things like carpets inside your house that are going to prevent heat loss by conduction. So loads of different things that you can put into your house. Also, you can have curtains next to your window. Those curtains will trap a layer of air right next to the window. And again, because air is a good insulator, just like down here, it'll reduce heat loss by conduction. So loads of these things you can put into place. I haven't got time to talk about the connection with this and payback time, so I'll come back to payback time when I do the second video. So I hope you found this one interesting. It was really heavily based on convection, conduction, radiation, evaporation, condensation, and heat transfer. That's a really big bit of the topic. Hopefully that's made it a little bit easier for you. And I'll cover the other half of physics in the next video. So thanks very much for watching. Post any further comments that you have on the comments page, and have a very good evening.